Hello, my name is Albert Otto, and I will be doing a summary on Chapter 6, Magnetic Confinement Fusion Energy, Bringing Stars to Earth. The primary topic of this chapter is how plasma research is important in the advancement of nuclear fusion energy research. So what is fusion? Fusion is the process seen all across our universe, in stars especially. Fusion is the process by which lighter molecules combine with one another to create heavier elements. And the way we produce fusion on Earth is through the collision of deuterium, which is hydrogen with one extra neutron, and tritium, hydrogen with two extra neutrons. The fusion of these particles outputs a helium nucleus and a neutron, as well as an immense amount of energy. However, because of the positivity of the nuclei of tritium and deuterium, a large amount of energy must be input to the system for the fusion reaction to actually occur. This is normally done by heating up the substances to high temperatures to increase the energy of the tritium and deuterium. When the fusion reaction is successful, it releases nearly 100 times more energy than what was inserted at the beginning of the reaction. The issue, however, is that not every collision leads to fusion. In order to increase the chances of a collision between tritium and deuterium, and therefore increasing the chances of successful fusion, high energy tritium and deuterium must be contained into a smaller space, or else the entire process would require an input of energy than an input of more energy than it produces. That's where plasma research comes into play. Because these processes involve protons, which are positively charged, making it a plasma, it means these particles have interactions with electric and magnetic fields through Coulombic and Lorentz forces. The chapter does not mention any specific details about the typical densities and temperatures of the plasma inside a nuclear reactor, but a quick Google search would reveal that the typical density is around 10 to the 19 particles per cubic meter, and typical temperatures are on the order of magnitude of 10 to the 8th Kelvin. Using these values, you can compute that the plasma pressure is about in the order of about 10 to the 4th. So, what research has discovered is that a very successful way to confine a plasma is by use of magnetic confinement, using a magnetic field to bind the plasma. The chapter discusses how in 2021, the tokamak achieved the best fusion performance so far, even generating up to 10 megawatts at Princeton and 16 megawatts at Culham Laboratory in the UK. The word tokamak is a phonetic merger of the words toroidal chamber magnetic coils. In a nuclear fusion reactor, a tokamak is a device whose purpose is to generate a magnetic field in the shape of a donut to contain high energy plasma materials. The way a tokamak works is by use of 3 electric coils which generate magnetic fields in different directions. Firstly, there is the inner poloidal coil, also known as the solenoid. The solenoid generates poloidal magnetic field lines. The next coil is known as the toroidal coils, which produce a second magnetic field whose lines trace out a torus. The first 2 coils together create a helical magnetic field that is used to contain a plasma within the tokamak. The third coil produces a larger poloidal magnetic field, which is used to size and shape the magnetic plasmas. Scientists in the industry using the concept of the tokamak are building an ITER fusion reactor with the goal of achieving controlled burning plasma. Burning plasma is plasma whose main source of heating comes from the energy released from fusion reactions happening within the plasma, leading to more subsequent fusion reactions without having to input as much external energy. Additionally, the use of burning plasma allows for the creation of more tritium, which can be made from lithium. This works because the neutron released from the deuterium-tritium fusion is not bounded by the magnetic field of the tokamak. So the idea is to capture these neutrons in an outer material to generate more tritium from absorption by lithium atoms. This way, the fusion process requires less external energy input, increasing the net energy generation. With all this given context, what is the societal impact? We are admittedly currently in a very scary point in human history, where recently the doomsday clock just hit 89 seconds to midnight, with climate change being a high factor as to why. A big contributor to climate change is the excessive emission of carbon in our atmosphere from our daily generation of energy. Successfully harnessing a net positive amount of energy from a fusion reactor provides a new, cleaner form of energy generation which does not emit an immense amount of carbon into our atmosphere. It is also likely become more efficient than nuclear fission energy. Fusion science has also contributed to many fields like material science, as there is still the problem of creating advanced materials capable of withstanding high temperatures, neutron bombardment, and intense magnetic fields. And a lot of science of fusion reactors can also apply to lots of physics research, like particle accelerators. All right, that's all for now. Thank you for listening to my TED Talk. And remember, fusion energy is great.